In this video, we take a look at our next counting strategy known as combination. We pick up where we left off with a question about light switches. 7 light switches are on a wall. How many arrangements are there in which 2 are in the off position? This is indeed a job for a non-distinct permutation. One way to think about the problem is to think about it like rearranging the letters of a word. So if I put an X for off and an O for on, I could think of this very boring word with 2 X's and 5 O's and just ask myself, how many different arrangements are there using all of the letters of that word? Because if I were to rearrange the word like this, then that would be a different pair of light switches that are turned off and a different 5 that are turned on. So I can work that out real quickly because there are 7 light switches, so that's 7 factorial in the numerator, and then 2 of them are type X and 5 of them are type O. So the answer would be 7 factorial divided by 2 factorial, 5 factorial. And that simplifies very nicely. 7 factorial is 7 times 6 times 5 factorial. And then I have 2 factorial and 5 factorial in the denominator. You can cancel the 5 factorials. And this is just 7 times 6, which is 42 divided by 2, so 21 ways. It turns out that this type of problem fits into a broader category of counting methods called combinations. By definition, a combination is the number of ways k things can be chosen from n distinct things. Notice that in the definition of combination, there is no mention of arranging or ordering whatsoever. And that's one way in which the definition for combination is very different than a permutation. Permutation is about selecting some number of objects and then rearranging them and seeing how many different ways that can be done. The combination, meanwhile, is just about selecting. We have a formula that we can use for combinations, and it's actually very simple to understand. I'll say NCK is equal to, I'm going to start with the permutation formula. NPK will be in the numerator. NPK is the number of ways that I can select and arrange all k of those objects. And in the denominator, I'm going to put k factorial because the combination, we don't want to actually arrange them. We just want to select them. And permutations select and arrange. So if I simplify this a little bit, I'll end up getting n factorial over k factorial times the difference factorial. And that's the formula that you can use to execute a combination when you know n and k. Let's see it used in an example. A group of 25 people run in a race. You might recognize 1 or 2 of them there at the front. The top 5 finishers advance to the finals. How many possible groups could advance? This is a job for a combination, not a permutation. And sometimes in counting, picking the right tool is half the battle. The reason a combination is the right job is order doesn't matter. If you finish in the top 5, you're good. If you don't finish in the top 5, tough luck. With a permutation, we'd be more concerned about how many different ways could the people finish the race, first place being distinct from second place and third place. But in combinations, the order doesn't matter. So what I want to work out here is 25C5. And that would just be 25 factorial, that's n factorial, over 5 factorial, that's k factorial, and then 20 factorial for the difference. Just like that. You can simplify this to 53,130, either by doing the multiplication by hand and canceling things out, or perhaps by using a calculator. However, very often combinations are large and you won't want to completely simplify them. So sometimes we'll just write our answer like this, 25 over 5, almost like a vector. This is a notation that means the exact same thing as 25C5, and it saves us the trouble of actually doing the mathematics, the arithmetic, I should say, to simplify it, much like if you were to write something in exponential form. In our next example, we're told that you can choose 2 of 7 princesses to visit your table at Disneyland's character breakfast. Who will you choose, and how many ways can you make the choice? So this is a job for a combination because we're just going to choose them. It doesn't matter which order they show up. If Cinderella's first and Ariel's second, or if Ariel's first and Cinderella's second, I still chose the same 2. So it'll be 7 choose 2, and I'll get 7 factorial over 2 factorial times 7 minus 2 is 5 factorial. And this is probably looking kind of familiar. 7 times 6 times 5 factorial over 2 factorial times 5 factorial. The 5's cancel. 7 times 6 over 2 makes 21. There are 21 ways you can make your choice, which is the exact same answer as the problem that started this video, which was the light switch problem. When you were thinking about the light switch problem, you probably weren't thinking about choosing things and combinations. You probably were thinking about arranging in different orders so that 2 were on and 5 were off, or vice versa. I forget which one was off and which was on. It turns out that these 2 problems are actually identical in structure. I can say this more generally, and this is a very important big idea. A combination, which is the number of ways you can choose k things from n things, it's equivalent to a non-distinct permutation with only 2 elements. You can think about those 2 elements as being in or being out, meaning you could think of them as being chosen, like light switch turned on, or not chosen, turned off. And so we see that there's an equivalence here between NCK, which is n factorial over k factorial times n minus k factorial, and the non-distinct formula that we came up with in the other video, which was n factorial over, remember, it's the types. So I might have type k1 factorial. I might have type k2 factorial. What the big idea is saying here is if there's only 2 types, right, in and out, then it must be true that k1 and k2 add up to n. And that's precisely what's happening with the combinations here. K and n minus k add up to n. It's an important idea to keep in mind. Once again, I'll leave you with an example to think about. See if you can figure out how you can apply your knowledge of permutations and combinations in general, counting in general, to answer this question. How many paths lead from the start, that's this corner right here, to the end? A couple rules. One rule, you're only allowed to move north and east. Otherwise, you could be walking around the block 7 times, and there'd be an infinite number of paths. So that would be a little less interesting and unproductive, maybe. So you got to get from the start to the end. You can only move north and east, and you can only move along the city block. So you can't cut through diagonals. You can certainly take a very jagged path like this to get there. As long as you're moving north and east, it counts. See if you can figure out how to use your knowledge of counting to work this one out.